Okay, Await 2.0. My name is Gor Nishanov. I'm a developer in Microsoft Visual C++ team, and I work on design, standardization, and implementation with many other people of stackless resumable functions, the most efficient, the most scalable, the most open coroutines of any programming language in existence. The best part, it is all true. If you don't believe at the end of the presentation in an hour, let me know. This is a continuation of proposals that we already had on resumable functions, and it was positively received at the recent concurrency study group, and hopefully it will get into C++ 17. But you don't have to wait for C++ 17 because experimental implementation is to be released in Visual Studio 14. Now you see those quotes. It means I am not supposed to give any promises, but it's looking good. So what are the coroutines? So first time it was mentioned in 1958. That is 56 years ago. And Melvin Conway, by the way, who have heard about the Conway's law? Whoa, awesome. Well, I just learned about it yesterday. And the law states that if 4 teams are working on the compiler, you will end up with 4 passes. Now, this is 56 years ago, so the pass was expensive because what you had a punch tape that will get into the, it will read the data from it, it will process the path, and then punch another tape. That's the result of the pass. Then you load a second pass, and you keep doing. So what Conway wanted to do is to be able to have the Cabal compiler in one pass. So you put your data from the one side, it churns through it, and outputs the result. And he wanted to make sure that people are still writing their passes in the same manner they were writing before. So essentially, when the first pass would be writing an output to the punch tape, actually it transfers control to the second pass that is actually suspended at a point when it is reading from the tape. So his definition of a coroutine was it's a function which behaves like a main program. Well, it's not very actionable. So 10 years later, Knuth gave more convenient definition, which is coroutine is just a generalization of a subroutine or a function. And you can think about it this way. So functions, we all play with them all the time. So they have essentially 2 operations for the purposes of this discussion. It has the call part where we pass parameters and where the function frame is allocated, where it keeps its locals and temporaries. And then there is the part where a function completes and returns result. At that point, results get transferred to whomever is waiting for it, the caller, and a frame is freed. So coroutine is just like that, with some little differences. But it also gets 2 more operations, suspend and resume. Coroutine comes in several flavors. So first pair of flavors are symmetric and asymmetric. So in symmetric coroutines, suspend and resume operations are glued together. So when you suspend a coroutine, you must at the same time to resume another coroutine. So it behaves more like a context switch. Whereas in symmetric coroutines, it's more I guess, user-friendly notion that it behaves more like a call. So you call a coroutine, it's suspended, it returns control back to the caller, and then at some point, you can resume it. And again, resume acts as if it's a normal call. And when the coroutine is resumed, it jumps right exactly where it was. And initially, it was thought that coroutines are, the symmetric coroutines are more powerful. Later, it was shown that actually you can express one in terms of another and vice versa. So essentially, it's just a matter of taste. And we have examples that modulo 2 Windows Fibers boost context. They could be a representative of symmetric coroutines because they implement context switch semantic, whereas C# implements asymmetric coroutines with their tasks and generators. Less interesting flavors are first class and constraint. Actually, first class is the good flavor. Constraint is the bad flavor. There is no we don't want to go there. Where first class means what you would expect. There is an actual thing in your language that you can return as a result, pass as a parameter, store in a data structure. Another useful set of flavors is stackful versus stackless. Essentially, it means how much state is preserved when you suspend a coroutine. It could be just that local, just the local variables and temporaries that are within that coroutine, or it could be entire stack. Another way to think about it is that unit of suspension in a stackless coroutine is that coroutine. Unit of suspension in a stackful coroutine, it's just an entire thread. So actually, if we combine those flavors, symmetric, first class, and stackful, well, that's user mode schedule thread. Whereas what we will be talking about is asymmetric, first class, and stackless. So I think the only thing we need to mention, why stackless versus stackful. There is a reason why people are trying to avoid threads. There is a cost associated with threads. Even if you switch to user mode threads like fibers, you still have to worry about the memory that is being reserved. It doesn't have to be committed physical memory, but at least you have to consume 1 megabyte on Windows and 2 megabytes by default on a Linux of the virtual memory. Whereas what you actually want, well, what is actually local to the coroutine is just those 2 green boxes, the locals and the parameters that were captured by the coroutine. And people realize that. Languages like Go, anybody from Google? Oh, look at that. Have you used Go? Excellent. So what Go is doing, and let me know if I'm lying. The last thing I've read is that they use 4K chunks. So stack is no longer contiguous. What you allocate stack in 4K chunks, and then in you instrument your function calls that before you call something, you check whether there is enough room in the current chunk, and if not, you will allocate a different segment somewhere, put a link to that, and then there have to be a check when you return. And there are other ways to do it without checks, but that would include like playing with say guard pages to make sure if you accidentally hit that page, you will automatically grow it somewhere else. And in stackless coroutine, that's just it. The entire state of the coroutine is just those yellow and green lines. And a coroutine, stackless coroutine, does not own the stack. It executes on whomever called it. So it borrows the stack of the caller. There is no context switch. So to help us to make this decision, these were the design goals we set for the coroutines if they were to be added to the C++ language as the core language extension. First of all, those coroutines have to be very scalable. They should scale to hundreds of millions of concurrent coroutines, well, and billions too. So it's like, no, we're going big numbers. They should be highly efficient. You should not have second thoughts about, oh, it kind of feels like a coroutine, but I don't want to like deal with all of it. No. It is suspend and resume is as cheap as a function call. So whatever the overhead involved in the function call, running the prologue, running the epilogue, well, that's what you have on suspend and resume, nothing more. Now, another point was we wanted to make sure that they seamlessly interact with the rest of the world. So coroutine from the outside looks like a normal function. You can call it from anywhere. You can call it from C. Similarly, if you are within the coroutine and calling the outside world, no restriction. Moreover, we made sure that you can essentially marshal the coroutine in a void star and then pass it to a C API set in a callback. You can reconstitute it and resume. Now, this is just a language extension, sorry, evolution. We don't define coroutine types. We just, compiler exposes very efficient mechanism to suspend and resume a function and exposes hooks to the library developers to invent high-level semantic they want to associate with the coroutine. And it's a paradise for library developers. And finally, for those people on Mars, JSF, and in Google who cannot use exceptions, we thought about them too. This feature does not rely on exception. It can help. It can use them to propagate errors, but it doesn't have to. You can design libraries in such a way that you completely avoid exceptions. OK, enough with the text. let's go to the fun stuff, code. So what I'm trying to write right now is I want to connect to some TCP port, open TCP connection, and read a bunch of bytes from it and see how many of those bytes contain letter C for some reason. So far, it looks like a normal function. And in fact, it is indistinguishable from any other function that has a signature. So the fact that it will become resumable in a few seconds, it's just an artifact of the implementation. The caller doesn't have to know. So far, we got a buffer of 64K. We're going to read in 64K chunks. We have a result in which we'll accumulate how many characters we counted. And now we're trying to establish a connection. I'm going to call asynchronous socket APIs. And while I'm waiting for the result, I would like to suspend that coroutine. To do that, there is a new keyword called await. Now, TCP connect here has to return a type which satisfies requirements of an awaitable type. So in this case, I wrote an adapter going straight to the C APIs on Windows. So after adapter is compiled away by the optimizer, it's just raw APIs to C. You don't see this adapter, actually, when you look at the disassembly. So at this point, coroutine will be suspended. When the connection is reached, I guess, it will be resumed. Connection will be returned and stored in that variable. And we now initiate reading, similar structure. We will count how many bytes we encounter that has letter C. And we'll keep looping and return the result. Now, this is essentially a zero overhead lightweight adapter over raw OS APIs. This execution of this function will incur only one memory allocation. And that memory allocation is for the coroutine frame. Because I mentioned that these coroutines are stackless, it means the state that has to be preserved between suspend and resumes cannot be on the stack. It has to be on the side. So what happens here is that all of the local intemporaries that you have in this function, they go into this separate coroutine frame. It has also some platform context, which could be just like one address. It depends on the platform what has to be saved on the context switch. Sorry. Not the context switch. It's just a suspend of a function. And this is compiler-supported feature. So compiler knows exactly which registers will be used across this await. And it can choose to save them and restore them around the await. And coroutine promise is what a library writer provides to explain the semantic of the coroutine. In this case, the coroutine returns the future. So we need to explain how to link the coroutine promise to the future. And that allows us later, when a result is produced, we set up in a promise, and it informs the future about it. Now, this will be the busiest slide of the talk, and this is on purpose, so that we'll experience pain right now, and it will become much, much, much easier later. So let's keep going. So we already talked about the suspend point right there. These are awaitable expressions, that the type they return have to satisfy this set of requirements. The promise, again, it's not a concrete type, it's a concept. Library writer have to conform to it, and then the compiler will correctly hook it up. And the last thing which compiler injects in the resumable function is there is an initial suspend point and a final suspend point. And again, a library developer decides whether this particular coroutine type need to be suspended before even entering the body of the coroutine. And also, before the destruction of the body, he can choose to either suspend the coroutine so that maybe somebody can read some value which is stored in the coroutine frame and then let it go, or just go straight and delete it. It doesn't look that scary. We only add 2 by 2 by 2 by 2 to the standard. And 2 by 2 by 2 means we're adding 2 new keywords, await and yield. We are adding 2 new concepts, awaitable and coroutine promise. And we are adding only 2 new types. Resumable handle, that is a function object that you can call, and compiler produces this resumable handle for you. And when you call this function object, coroutine is resumed. And a library writer, a library developer, can define specialization of resumable traits to explain how to hook up compiler, suspend, and resume to the machinery that library provides. And we will look at an example of that later. OK, more examples. And before I go into more examples, anybody has a burning question I can answer?
Is it standard await, or is it just Microsoft invention now?
Well, this is a proposal for the standard. So we really hope it will get accepted. It's awesome.
So there's talk of Boost as I/O.
Yes.
I/O going to the standard. It has its own asynchrony mechanisms.
Yep.
How do you think the committee would reconcile this with that?
They are orthogonal. This provides an efficient way to suspend and resume a function. Now, Boost ASIO, oops, I'm sorry, I need to repeat the question. So the question was how to reconcile this proposal with Boost ASIO. Actually, they're complementary. Boost ASIO, Christopher Kochloff, he even implemented stackless coroutines using macros, using a Duffy device. Now you don't have to worry. You just plug in the proper stackless functions, and they will just work together. And that's why the focus is on the library developer. We are exposed tools, and library enthusiasts can go and play with them, write adapters, or just make their libraries compatible. You can go any way about it. Yes?
So if you pass variables by const ref that are on the stack to one of these things, that's probably a no-no?
The question is, what if the variables that we pass to a resumable function are passed by a const ref? There could be a warning, but maybe there is a case where it is actually acceptable. In a few slides, I will have an example where it's perfectly reasonable to pass something to a resumable function by reference. And const reference is just a small step from it. Yes?
Will users be able to override the allocation for the coroutine?
Absolutely. The question was, will the users or library developers to be able to override the allocator type that is used to allocate the frame of the resumable function? Yes. And also, compiler is allowed to elide allocations if it can prove that the lifetime of the coroutine is such that it can use the stack memory of the caller to put it there. OK, let's start with a simple example. We want to write a generator that will be used in this fashion. What I want to do, I want to print all Fibonacci numbers which are less or equal to 10. And because I don't know, how big are the Fibonacci numbers, I will compute, just in case, 35 of them. Now, what requirements are on Fibonacci? It should have begin and end, and it should return an iterator which is even weaker than input iterator. But let's say the Fibonacci has to return begin and end, which returns input iterator. This is how you would write such a function. So we will have, it will look like a normal function, and the yield would be a point where we will suspend this coroutine and let the guy who is trying to pull the value from on this side to get it. And just to expand a little bit so that we can talk in slightly more details, is that arranged 4 is expanded by a compiler into something like that. Or at least it has to behave as if it is expanded in this manner. So let's look at the first point here, Fibonacci 335. So what happens is that we call into the Fibonacci, into this coroutine, and generator, the guy who wrote the generator, demanded that he actually wants to suspend the coroutine on creation. He doesn't want to enter the body, because maybe that coroutine is trying to compute 42, and it will take 40, many millions of years. So unless somebody pulls it, it's not. We don't have to burn the cycles. So in this case, what will happen is that on entry of the Fibonacci, we will allocate this coroutine promise and other things which happen to be in the frame, and immediately suspend. And the generator will have some kind of link, a pointer to the coroutine promise. So this is what happened when we were doing this one. Fibonacci 35 going to range. Now we'll initiate a pool, range begin. So range begin return an iterator. And in its constructor, it will resume the coroutine, and it will run until the yield. When it hits the yield, this value A goes in the current value, which library designer chose to store it. And now there is here there is a choice. If the value is small, it could be just a copy. If the value is big, it is just fine to store an address to the temporary on the stack, because now we can actually give to other people addresses to our local temporaries because we are suspended. We don't have to allocate stuff on the heap. Well, sorry, go back. So, right. We hit the yield. Value A is stored as a current value. Then here we're trying to extract that value. And iterator here would just go inside and dereference its value and gives it out. And this loop keeps repeating. Now, the interesting thing will happen when we're trying to break out of the loop. Because at this point, our coroutine is probably like on iteration 5. And it still wants to go 30 more. Well, what would happen is the destructor of the generator, and again, I'm just describing a library writer, what a library writer can do. That is not what is in the proposal. He can set a flag. He can set a flag, canceling, and then resume the coroutine. And that flag will be checked by the yield operator. And if it is canceled, it goes to the end and destroys everything. And now, we don't use exceptions for that. That is one point how we're safe in environments where there is no exceptions. And there is another good reason why you don't want to use exception, because right now, this is just plain control flow. I'm doing break here. Why do I want to do a trap in the kernel and throw an exception just to fulfill this break? OK, another example. Now, as an exercise, can you tell me what will it print? OK. Yes, yes. So the answer is it will print numbers from 0 to 99. But I wanted to show you because this was the simplest example of a recursive generator. Normally, you would use that to flatten a tree, because essentially what you are doing, you have a tree, you do a recursive traversal of a tree, and you flatten it into a sequence. So you can do funny things like check for this. OK, I forgot the name of the algorithm, but it's, do you remember it? No. OK, so you can do recursive generators, because not only you can yield a value right here, but you can also yield entire generator. So at this point, it will yield whatever the next invocation of the generator will do. OK, what is this? Yes, yes. So because Fibonacci is frequently abused and computed in horrifying ways in various examples, I wanted to make sure that this is, whatever I'm going to show is not a good way to compute Fibonacci. It's probably one of the most expensive ones, because this one computes Fibonacci in constant space and in just log n step. Hold on. What I'm going to show you, how to compute Fibonacci in 1.6 billion recursive invocations of the coroutine, and in under 20K of space. So don't do this, but you can. And this was inspired by Pablo's talk this week. So what we have here is we just invented a coroutine type spawnable. And it's kind of like a future, but it interacts with a scheduler. So when you say get on it, it will say, well, I don't have a value yet. Let me schedule it and run it. Now here, we have an operation plus on 2 spawnables. Now, if you do it naively and you will schedule the left-hand side as the worker and the right-hand side as the worker, suddenly you have an explosion of workers. So you will run out of memory at about Fibonacci 35. But what you can do, again, you can, as a library writer, can say, you know what? I want to suspend on creation of the coroutine. So in this case, Fibonacci n-1 and Fibonacci n-2, it is kind of like a lambda capture. It captures the parameters, but it stays right there. It is not running yet. Now we can safely schedule the worker for the second half and let the current thread just dive into the first part. So now it's linear. Now as we go down, it will schedule one more worker. And this expression will suspend the parent until both sides of the plus are ready. Yes, yes, it's a very good way to compute Fibonacci. 1.6 billion of recursive invocations. And this is also our stress, how we can make sure that our coroutine creation and destruction is very, very fast. This is another scale, but now a scale stress test, but in a different dimension. So Google invented the language Go. And the idea was to simplify concurrent programming, one of the ideas. And how they go about it, they have lightweight coroutines called goroutines. And you connect them with channels. And there are various flavors of channels, but the one I want to show here has a rendezvous semantic. So channel has no buffer. When you're trying to push into the channel and nobody is reading, you will get suspended. Similarly, when you're trying to pull, there is no writer, you're suspended. But when those two guys met, they both resumed and go happily. So here you go. This is the goroutine in C++. What we have here is some type that says it's a goroutine, and it gets 2 channels by reference, left channel and right channel. And let's create 100 million of them. And what I want to do is essentially I want to create 100 million of goroutines, 100 million and one channels, and make sure that every coroutine is surrounded by a channel, and there is stop. Yes, and there is like one more channel. What I'm doing, I'm pushing 0 on the left-hand side channel, and it travels through all of the 100 million goroutines, suspend and resumes increment 1. So you can say that this is the most. The most is just an expensive way to print number 100 million, but that's what it's doing. And it's doing it reasonably fast. It takes about 30 nanoseconds through every step of the chain, and we haven't yet spent time on optimizing the compiler. Comparatively, like call to a no function is 2 nanoseconds. So it's about 15 times slower than call to a function that does absolutely nothing for comparison. And of course, context switch is in microseconds. Right, and all of those examples are just examples of what library writers can do with this mechanism. So this is a library designer paradise. Front-end developers work hard to give you syntactic sugar. Back-end developers work hard to make sure that suspend and resume only touches and saves registers and restores that are actually used in that particular function. And then library designers can party. They can invent new types, or they can adapt to existing types already. So it is not limited to the new types you invent. You can adapt coroutines to ERPs in the kernel if you feel like. There are 3 levels of using the coroutines. One is you just use them as a plain user. So we saw those examples that somebody else provided the coroutines and all of the adapters, and you just use them. That's easy. The most hardcore way is invent new coroutines. So you need to know then like most of the stuff that was on this busy slide. But then there is this moderate level. Because what if you already have excellent coroutine framework that provides you with lightweight tasks? but they missed one particular API that your operating system has, or maybe some new library which has asynchronous APIs. So you want to adapt await to them. How do we await on things that await doesn't know how to await upon? Well, inspiration for that is, wait a second, did it go? Yes. Inspiration for that is arranged-based for. This is just a reminder of what happens when you have this in your code. This is roughly what compiler is supposed to do. Well, another point here is that begin and has special lookup rules. If they find begin or end inside of your class, they will use this form. If they didn't find, they will use essentially standalone begin and end that they looked up in the namespace of your type. So similarly, if expression is of a class type, we will start looking for await ready, await resume, and await suspend in the scope of that class. And if either of them are found, this is an equivalent of what will get generated. But this is actually an expression, but I do it as a block because it's just easier to read that way. So we grab a temporary so that we can refer to this expression several times. And we will ask, is this thing we're awaiting upon is already ready? We don't even have to go and do suspend. And if so, we are resuming the function, and we would like to unpack the result of that await. So result of the await operator is whatever the await resume returns. It could return a void if it's just, it works like a statement. Or it can, for example, unpack the result of the future. So if you're trying to adapt to a future, you will just call .get. Of course, it will bring exceptions. There's a way around it. I'll show it later. Now, if whatever you're awaiting is not ready, you will go inside, and compiler will synthesize this resumption function object, and will call await suspend, and here where your adapter is supposed to subscribe in some manner continuation so that it can be resumed. And finally, once it's done, this is suspend point. And at this point, you just jump to the epilogue, and the function exits without destroying anything. Everything stays as it is. When later somebody calls resumption function object, you jump right back here and restore all of the registers, whatever they have to be restored, and you continue the execution. Otherwise, you use the standalone functions to do the job. OK, what name would you give to this awaiter? This is trivial awaiter number 1. Or what will it do if you await on it? OK, nothing is one answer. More? OK, excellent, very, very close. Another answer was wait forever. Well, yes, I probably should have told that potentially, like especially in a generator example, you don't have to continue by calling the function object that was given here. You can actually have another link to the resumable function, which is stored in the generator itself. So essentially, I would call it suspend always. So if you say await suspend always, you immediately suspend. Without, yeah. If you can resume the function using the coroutine return object, you can resume. Otherwise, you suspend forever. This is suspend never. They're useful classes. I will show them shortly, but they're useful, but they're trivial. How about simple awaiter? Here, I'm trying to write an awaiter which will do the following. I want to write a function which gets a mutex by reference. And if I am able to acquire it, I will just execute the code right here. But if I am not able to acquire it, I would like to suspend this coroutine. And whenever we are able to acquire this mutex, we will resume it. And I will do it in a very, very naive manner. So what I would do, I would create a member variable, unique lock, and I will try to acquire it in the constructor. Try to lock is a nice tag parameter for the unique lock, which says, please try to acquire, but if you couldn't, just leave the lock in unowned. Sorry, just know that you weren't able to acquire the lock. Await ready will be very, very simple. It will check, did we acquire the lock? And if we did, we just jump to the end. And jump to the end, well, we move out the unique lock so that it will be returned from await expression. Now, we can talk about, in the future, doing some kind of RVO, return value optimization across the await. Right now, not yet, but this is how it works. And finally, I will do very naive implementation. If I wasn't able to grab the lock, I will spawn a thread. I will give it a pointer to this and a callback, and then I will try to lock a lock on that thread. And if I succeed, I will just call the callback that will resume the coroutine. So this is simple awaiter number 1. Simple awaiter number 2 is, I'll probably go very fast. It's, let's say we have existing type boost future. And let's say, oh, I'm sorry, there's a question.
In the previous slide, is it really okay to return void from using, or do you need that to be type which void something?
Are you talking about await suspend?
And do something.
OK, the question is, how come here I return void? Why don't I return like goroutine? You know, you're right. But I assumed that the library writer provided specialization of resumable trace to say, you know what? If the function returns void, use my coroutine machinery. But yes, good point. Yes?
Are your function context objects copyable?
The question is whether the coroutine, how do I call it? A coroutine frame is copyable. No, it's fixed in memory. And the reason for it, imagine that, because this context contains the variables that you have inside of that function. And you can imagine that your code says, you know, int star equal address of something else. So you really, you cannot move that. Once the resumable function starts running, you cannot assume that you can just take this piece of memory and move it out.
Why are the functions? Why is it not make on object-based everything like methods?
Well, I was using function in the OK. The question was whether this is only limited to functions, right? Of course not. No. What I meant is that what is a lambda? A lambda is just a struct with the member function. And what is the member function? It's a function. So yes, it's applicable to functions, member functions, static functions, lambdas, anything you want. Lambdas of lambda instead of a lambda. OK. I think this is it's all one-liners. How to adapt await to deal with the future. Is ready, do dot then, and give the callback. And in resume, we'll do dot get. So far, we were in the C++ land. OK. How about we start interacting with C APIs? Well, to do that, I need to, yes, we covered so far await, awaitable. I need to explain the resumable handle a little bit to explain how to work with C APIs. A resumable handle defined as follows. So we have this. It is templatized on the promise. And by default, if you don't care about the promise, it's assumed void. So void, the resumable handle specialized on void. The only thing you can do with it is essentially call it. And when you call it, the coroutine is resumed. But it allows you to convert the coroutine handle, resumable handle, into a void star. And then you can reconstitute it back when you need to. And that's what I needed. For completeness, this is what full resumable handle is. And it is doing everything which is the void version is doing. Plus, it gives you an access to a promise. OK, so what I want to do, I want to suspend my resumable function for 10 milliseconds. And this is how I want to write it. And I already prepared the room for the rest of the implementation. So let's see. In the constructor, we simply grab the duration and store it as the member variable. Await ready, again, very easy. We will check whether we actually need to suspend. And if so, we will not even suspend at all. Otherwise, now I'm no longer saying template F. Now I know what the type is. The type is the resumable handle. And I need to know that because when I create thread pool timer and give it a callback, I need to give it void star context. And I used 2 addresses to get there. Now, how the timer callback looks like, I don't care about the first parameter, last parameter, but I care about the context. I reconstitute resumable handle from address, from context, and then call it. Done. Now, when the timer fires, my coroutine is resumed. Now, I just need to do a little bit of housekeeping. I need to actually start the timer and pass the relative count. On Windows, I'm using secret knowledge that the underlying data structure of the system clock duration is the same that NT uses. So I'm just casting it to in64 and doing negative because that's how you express relative time. So last line here, I created the timer. I started the timer, and it will fire this callback in whatever the duration is. And I do absolutely nothing in await resume because it looks like a statement. And finally, in the destructor, if the timer was created, I'll close it. Yes?
Do you call the resume function in another thread?
Absolutely. You can, the resume function, stackless resumable, okay, did I repeat the question? Okay, the question was, is it okay to resume a function in a different thread? The answer is yes. Language does not impose any limitation. Resumable function runs on the stack of whoever called it. Now, if you are implementing some kind of library framework, you can decide whether it's okay in that framework. But from the standpoint of the language, doesn't matter. Yes?
Can you reuse the awaitable things? Like, can I say auto sleep for 10 milliseconds and then await, put in a variable and then await on the variable?
Great question, great question. So the question is, well, let me do my interpretation. Here, you're doing it very inefficiently because you are recreating a timer every time you wait. I'm not sure about the leaks, but it's absolutely wasteful. If I do this sleep in a loop, for example, right, I will do a lot of extra timers, not needed. So yes, if your pattern is such that you would like to share a timer, for example, you can create a timer class, timer object, and then you will create a sleep4 as the member function on that timer object. And the timer object will return you an awaitable, which will essentially reuse the timer stored in the timer object. So you will say, may or foo timer class a or timer, and then you say timer.sleep4. Well, was I able to answer your question?
Not really, because what I meant was if you have like the sleep4 itself and put that into a variable, like an object of the type sleep4, and then await on the object, and you do that multiple times. I mean, that's not a good example for the sleep4, but if you have another awaitable that perhaps produces some data and then returns after the await, and then you await again on it and produces some other data. Same object.
OK, this is interesting. I haven't played with it. Let's discuss that at the end. Yes, you can do that, because this is all normal objects, normal expressions, and the only thing that happens is that await is expanded in a funny way. Yeah.
On the previous slide, where it says awaiter, is that supposed to be sleep4? Yeah, do I understand that right?
Let's see.
Destructor.
Oh, right. Thank you very much. So you got a mistake on my slide. Yes, because I actually refactored this class from a different. It was, well, I'll explain. So what I was trying to do is I was having a function sleep4 that will return an awaiter defined as the inner class, and that was what I was returning. But later I was looking at it like, why I'm having an extra function around this class? I can just rename the class sleep4 and it will just work. Okay, so we are covered that. Let's go for the hardcore. We're close to the end. Let's just jump in. So, yes, thank you. When compiler sees a function with a signature, it will specialize the resumable traits in this manner. Essentially, it will say, OK, this is a function with this return type, and those are the type of all of the parameters. And it will see what it finds. And there is a primary template defined in this manner. So essentially, it says that, well, you know what? If you didn't provide any specialization, I will assume you want stand default allocator. And I will assume that whatever the return type, it has the subtype called promise underscore type. Moreover, if you provide your own specialization and you are fine with default allocator, you don't have to define it because we sniff it in the same manner how allocator traits fill out the default ones if you don't provide them. So I'm not going to describe the requirements on the promise type. I will show it as an example. So here I'm trying to show what does it take to create a coroutine that essentially an asynchronous task that returns boost unique future. So let's see. So it says, yep, if the return type is boost unique future and whatever else is there, I don't care, I will define the promise type as follows. I will stick the actual boost promise inside. And get return object is used by a compiler to find how to link the future with the coroutine, how to link coroutine return object with coroutine promise. And in the case of the promise future pair, I will simply call get future. Set value, I will just forward to the promise. Set exception, I will just forward to the promise. And I think those three functions can give you a hint why we called this coroutine promise, because so far it looks pretty much like a promise. It has a few more members, initial suspend and final suspend, and that's where those trivial awaiters come through. If you don't want to do anything funny, it's fine to say suspend never or suspend always. And finally, I don't have any support for cancellation. I will just return false all the time. So it's, and there will be a slide which explains the cancellation. So it's actually a useful thing. And generator, remember how many slides ago we had a generator example and it was bailing out of the loop? Well, what generator is doing in its promise, it says, oh, if I'm being canceled, return true. And and let's see. Oh, well, I'll show you soon whatever I was going to say. Okay, awaitable and exceptions. Now I want to show how we can avoid using exceptions. So far, our adapter over boost future was calling .get, right? And .get, if there is an exception, we'll just throw it in your face. Now, in resumable function or in tasks in general, you have this constant boom, boom, boom. What I mean by that, we waited for continuation. We got the completion. It has an error. OK, I will rethrow it. Immediately, at the block that surrounds the task, I will catch it, package it as the result of the task, resume the task which is waiting, which explodes and collapses, explodes and collapses. It's just so, OK, sorry. I don't like it. So how we go about it? It's very easy. We need to change one function here to enable to work without exceptions. And the function is, OK, who thinks that we need to change await resume to avoid exceptions? OK, who thinks that await suspend. Okay, I guess everybody thinks that it's await ready. No, it's not await ready. It is actually await suspend. So before we started with just f, we didn't care what the function object is that the compiler gives us. Then we graduated to resumable handle of void because we wanted to interact with C. Now we go full power. We actually know that compiler carefully gave us access to the promise in the enclosing resumable function. So what we will do, you see here I was ignoring result parameter, which .then was given me. Now I will see if the future has an exception. And if so, I will extract this future and store it in the promise. So this is one part of the answer. We need a second part. This is the second part. Which line should I change to make it work? I mean, okay, which half of the screen? That would be easier. One idea was get return object. No, it's the second half. Let me show you. We just need to change actually one expression. Before we were saying we don't care about the early cancellation, just use exception essentially. But if we care about early cancellation not using exceptions, then we can do this. Because every await here contains two different paths it can go. It can go straight, or it can go to the end. And cancellation requested is that flag which compiler checks which way it needs to go. If we return if we return false for the cancellation check, this check is optimized out. It doesn't exist. So there is no overhead. So you can use exceptions and be happy that on your normal path, there will be no checks. But if you don't want to pay the cost of the exceptions, you can actually have if error go to end at every await and yield expansion. And this is just, I was waiting for a question. But since we're close to the end, I will just ask the question and answer it myself. Well, but how would you handle an error in a case when you cannot use exceptions that occurred while you were trying to subscribe continuation, right? For example, I'm trying in my await suspend to create a timer, and we ran out of memory, or whatever other reason why timer wasn't created. Now I need to say, please, please, do not try to suspend. Nobody will resume me ever. So it is solved by saying that it is OK to also return a Boolean from await suspend. And the Boolean will tell you if actually the thing we're trying to do in the launch succeeded. So this is how you express an error during suspension without exceptions. With exceptions, you just throw. We're done. Questions?